Right. The purpose of this lesson is to have a little bit more of an in-depth look at how nucleophilic substitution occurs. As it turns out that actually there is more than one mechanistic pathway by which a nucleophile can substitute the halogen atom on a halogenoalkane. And this is actually dictated somewhat by the type of halogenoalkane that you have present. Now, all of this particular bit of theory is from the A2 side of the course. However, understanding the principles here will help to explain some of the patterns that you are expected to know about in the AS side of the course, in particular with regards to the reactivity of different types of halogenoalkane. So we're going to go through this now, and there will be, of course, time to revisit later on in the course as well, and hopefully this will just cement everything quite clearly. Right, so we will start off just recapping the form of nucleophilic substitution that we've encountered already, and this is known as SN2. Okay, now SN2 is the form of nucleophilic substitution that would be preferred by primary halogenoalkanes. These are halogenoalkanes where the carbon in the CX bond is bonded to at most one R group, one alkyl group. That means that it has at least two hydrogens directly bonded to it. Okay, now in the mechanism, we have a one-step reaction where our nucleophile, which I'm just representing with the symbol here, Nu, again, that is a common representation that you will see elsewhere. We've got a lone pair here. The nucleophile directly attacks the delta positive carbon, causing the carbon halogen bond to simultaneously break. This then results straight away in the formation of your products. So you end up with your nucleophile now attached onto the carbon, and the whole molecule ends up actually inverting its shape. You see the tetrahedral shape that you started off with kind of gets flipped inside out like an umbrella, and you've got your X minus ion released at the end of it. So important to note here that this is preferred by primary halogenoalkanes. Okay, now the second mechanism by which nucleophilic substitution can occur is SN1, and this is the mechanism preferred by tertiary halogenoalkanes. Now, a tertiary halogenoalkane, in contrast to a primary halogenoalkane, is one where the carbon in the carbon-halogen bond is bonded to three alkyl groups. So I'll label those as R1, R2, and R3. Now, counterintuitively, SN1 actually is a two-step mechanism. You will learn about why the two mechanisms have these designations SN1, SN2 when you go on to further kinetics as part of the A2 course. So, the first step of the reaction actually occurs spontaneously. You wait around for a little bit of time, and the halogenoalkane molecule eventually, due to random factors, attains enough energy that the carbon-halogen bond just spontaneously breaks, and both of the electrons in the bond go towards the halogen. This results in the formation of a tertiary carbocation. Now, you've encountered these in the electrophilic the electrophilic addition mechanism. And you'll remember that a tertiary carbocation, such as the one that you see here, is stabilized due to the presence of 3 inductive effects from the 3 alkyl groups. Each alkyl group is able to donate a little bit of electron density to that central carbocation, and therefore the positive charge is actually spread out over the entirety of that species. The second step of the reaction is, of course, that our nucleophile is going to be attracted towards the carbocation and its lone pair is going to attack, resulting in the formation of a new bond. So we end up with our 2-step mechanism being completed. Of course, at the second stage, we, just as in the first one, release an X- ion, which is then going and floating around somewhere within the solution. Okay, so important to note for SN1 that this mechanism is preferred by tertiary halogenoalkanes. Right. In terms of the rationale as to why there is this preference, we will come on to that later. Okay, that's the end of that lesson. Right, with that additional background theory covered, we can now make a quick discussion of the patterns of reactivity in the halogenoalkanes. Now, the first pattern of reactivity that you need to be aware of is the pattern with relationship to which halogen is present in the halogenoalkane. So, number 1, reactivity dependent on the halogen. Now, what you will see here in terms of reactivity, most reactive, you will have the Ri, the iodoalkanes. These are then more reactive than RBr, the bromoalkanes, which are more reactive than RCl, the chloroalkanes, which are then more reactive than RF, the fluoroalkanes. These practically do not react via nucleophilic substitution. Or at least they will not be hydrolyzed. Now, the pattern of reactivity with regards to the type of halogen in the halogenoalkane is relatively easy to understand. And it is all to do with the carbon-halogen bond. Okay, so if we change the size of the halogen, which is the primary thing that is being altered here, going from large halogens to small halogens, this affects the length of the carbon carbon-halogen bond. So, larger halogens gives longer CX bond. Now, if your CX bond is longer, that means that the shared pair of electrons in the bond, the bonding pair, is further from the nuclei of both atoms. And this means that the bond is weaker. As the CX bond is weaker, that Well, given that this bond is something that has to break during the process of nucleophilic substitution on a halogenoalkane, this therefore makes the reaction occur quicker. So easy enough to understand on this one. The bigger the halogen, the longer the bond between the carbon and the halogen, the weaker the bond, and therefore the quicker the nucleophilic substitution. You can say that the activation energy for the nucleophilic substitution is going to be smaller because less energy is required to break the bond needed for the reaction to occur. The second factor that you need to be able to explain is the reactivity of the halogenoalkane as dictated by where the halogen atom is bonded in the chain. Now, at this stage, you need to be aware of three different variants of halogenoalkane structures. First of all, you have the primary halogenoalkane, where you've got your carbon bonded to the halogen. There is at most one alkyl group, and all other atoms bonded to the carbon are hydrogen. So here is your primary halogenoalkane. Then your secondary halogenoalkane, where two of the groups bonded to the carbon, bonded to the halogen, are alkyl groups. So we can label those as R1 and R2. So this is a secondary halogenoalkane. And lastly, you've got the tertiary halogenoalkane, which of course has three alkyl groups, R1, R2, and R3. Now, of course, you should remember that R is just the standard organic chemistry way of denoting a carbon-hydrogen chain. It can be any particular length, but as long as that is a carbon-hydrogen chain, you can label it as an R group, or also known as an alkyl group here. Right, now, the thing that this causes variance on is the amount of inductive effect that these alkyl groups give towards the carbon in the carbon-halogen bond. So in a primary halogenoalkane, we have one inductive effect, whereas in a tertiary halogenoalkane, we have three inductive effects. And this, you may begin to see how this may be relevant if you think a little bit about not SN2 but the SN1 mechanism, because you know via SN1 you form a carbocation when the halogen breaks off. So in the case of a primary halogenoalkane, we would form a primary carbocation. In the case of a secondary halogenoalkane, we would form a secondary carbocation. And in the case of a tertiary halogenoalkane, we would form a tertiary carbocation. Okay, now the pattern, of course, is that you have increasing stability. As you go from a primary carbocation to your tertiary carbocation. Now, as you remember, with the mechanism of electrophilic addition, the more alkyl groups you have attached to your carbocation, the more inductive effects are contributed towards that carbocation. So the more electron density is pushed towards it, the more the positive charge is spread out within the species, and the more stable that species will become. And this is important with regards to a mechanism which involves a carbocation intermediate, such as electrophilic addition, such as nucleophilic substitution via SN1, because your carbocation intermediate needs to stick around in the reaction mixture for long enough for the reacting species to come along and attack it. And in the case of SN1, we are waiting for our nucleophile to attack the carbocation to complete the mechanism in the second step. So the tertiary carbocation, which would result from the tertiary halogenoalkane, is more stable. Therefore, there's a better chance that it will persist for long enough for the nucleophile to attack it and therefore complete the reaction. So, tertiary halogenoalkanes generate tertiary carbocation intermediates in SN1. It's important, it is only in SN1. These are more stable due to increased inductive effect due to more alkyl groups. And more spread out positive charge. And the last point that we can make is more time for nucleophile to attack to complete the SN1 mechanism. Okay, hopefully that's clear enough. There is quite a lot of information here, so I would recommend going over it a few times, perhaps using another source of information to consolidate your understanding of this. The next thing that we will be covering after this point is to look at the reactions of the halogenoalkanes with ammonia, which again is a nucleophilic substitution mechanism, and we're going to focus only on SN2 for that one. But there is some level of complication within it. Nothing more necessarily than, for example, the hydrolysis reaction with water, but there's a little bit of additional detail that we need to cover with regards to the behavior of ammonia and the product from this reaction. Okay, I hope that's all been clear.